Yes, my name is Cassandra Smith, and today I'll be talking about the build system that I've been working on with a larger team, but it's called Quake. A little bit about myself. I'm really into programming languages. Previously, I worked a little bit on the Rust project. Really enjoyed that, primarily stuff with cargo, but in general, I just really enjoy programming language theory, Rust, Haskell, you name it. And that sort of got me into build systems and got me thinking about it. A lot of the work I did on Cargo. Cargo has a certain philosophy, and there's also a lot of things that people are doing. A lot of these past talks, like Diaxis, were talking about some of the advancements that have been made in Rust application development. And some of those really push the limits of what's possible in Cargo. And that's sort of how I ended up here. I work with the Robius project on various different projects. So there's the Robrix matrix client, and a few other things. And we do a lot of talking about how we can improve the state of application development in Rust as a whole. So here's why I am interested in build systems and why I think that maybe you should be as well. So application development is accelerating at a very high rate. There's been so many different cool projects announced, even like the past week. A lot of really interesting projects talked about just at this conference itself. But the actual tools that need to support it, build systems, languages, tooling, they don't get as much attention because they know they're not as flashy, but they're incredibly invaluable. Even if AI is doing 90% of the work, ultimately we still need something to compile the code. We need something to be able to reason about it, be able to verify it, and that will be a constant, I think, for a while. And I think if you're working on development tools, you'll also make a lot of friends because people will appreciate that. And also I think that the actual theory that's involved in build systems or just language design in general has its own value. And I think it provides more insights into how we can actually be able to develop for the future and sort of even what to develop, what to focus on. So this is sort of the key problem that I've started to notice as I've been working on this project and just been thinking about it in general, which is that build systems are sort of thought of, they're used or designed or chosen backwards, which is a sort of a weird idea, but the process kind of goes like this in practice. You sit down, you decide maybe what you want to work on, you have human requirements, and that ultimately drives the choice of which build system you might end up using or developing. And so, for example, if you're just working in one language, say Rust, you'll use Rust C and Cargo, but then you might find that your needs kind of start to expand outside of that. Maybe you need to, pull in some assets, or maybe you have a multi-stage build process, and then you need a specialized tool. If you're working on, say, a JavaScript, TypeScript project, or maybe a native one, like React Native, or some of the stuff that's being worked on with Expo, you'll end up needing to get more tooling for that. And because you probably have project deadlines, it ends up being that you develop these sort of ad hoc build systems in a relatively short amount of time, just in favor of those immediate goals that you're targeting. And in the process, a lot of people end up working on they end up building the exact same build system in a lot of different companies, a lot of different teams, a lot of different languages and frameworks. And they can be really good at one particular task or one class of tasks, but ultimately the whole industry will suffer because people aren't collaborating, people aren't thinking about the overall problem, and you just kind of end up in a state where you're always just having to reinvent the wheel, and the wheel isn't quite good enough in the first place. So here's how I have started to think about build systems. Their fundamental role as sort of a transformation of requirements, both human requirements and technical requirements, and everything in between, to actual mechanical procedures. So the requirements could be things like, what are we building, what components? They could be our front end and our back end, but it could also be like the different dependencies that we have. It could be the framework you're using. And then there's how those components actually relate. So the dependency tree is a pretty good example of that, how you can resolve different versions, how that all will end up structuring. And if you have different features you want to be activated, how does that cascade through the entire thing? And then there's also just how they should be built, in what manner they should be built. So are you targeting a particular platform? Are you doing a production build? Are you doing a development build? That kind of thing. And then procedures is just really, like I said, the mechanical sequence of operations or sequences of operations that need to be performed in order to actually achieve your actual requirements, and also sort of how to perform them. And you can be aware of the procedures, but ultimately they should be driven from the requirements. Sort of going a little bit further, you can also ask, like, sort of what are we ultimately trying to achieve? And that's really what your first question should be, hopefully. But also, what are you going to want to achieve 6 months from now? How is your project going to evolve? Is your build system that you're using, or just the design of the project itself, going to sort of fit that in the future? Are you going to have to rewrite it? Are you going to have to do a bunch of refactoring? And then on the sort of the other end, on the procedure end, sort of where the build system hackers might be thinking more about is, how can this process be streamlined or made more efficient? So running it on parallel builds on a fancy like computing server, or caching different artifacts and pulling them down so that everyone in your company can get like pre-cached artifacts and be able to build faster. And you might want to be able to sort of introspect into that process. So if you're doing like, say, a build system that sort of runs in CI/CD, you might want to be able to reason about, like, okay, what's the status of the process? What things failed and where did it fail, and why did it fail or succeed? So some things make this a little bit more difficult as well. These are the confounding factors. So multiple languages and their associated build systems or tooling are also frameworks as well. Targeting and bundling for multiple platforms. These days, it's a little bit easier to target multiple platforms or cross-compile, but the actual process of bundling is pretty difficult, because now you have signing, you have a whole bunch of different things. You have notarization for Apple-targeted platforms. And that definitely makes things a lot more complicated. Like I mentioned earlier, asset handling is another big one. Most compilers for languages, or most build systems, they're designed for code. That's what the people working on them are thinking about. This is maybe less the case for web, but I think the problem still shows up there quite a bit, even still. You take a look at like projects like Webpack, where it's sort of like people realize this. There's probably at least 20 different competing solutions, but that can be a real problem, because handling assets isn't just putting them into the artifact. It's also doing different operations. If you have, say, your logo as an SVG, you might want to scale it down or scale it up or whatever, or rasterize it for different icons and different platforms. Assets could also be data. You might want to do some data wrangling at the like build point, and that's a whole problem. And also, like I mentioned earlier, just sort of the different flavors of tasks. So you have building and different types of building. You have sort of just unit testing, but also just checking and verification more broadly. And then the actual deployment, and that's sort of where you might think about like CI/CD again. And I think evolution is really where this problem starts to pop up, and oftentimes, when you're 6 months down the line after you've started working on a project, this is where this hurts the most, because the actual requirements that you may have in the future are really hard to anticipate, and they're ever evolving. And when those new requirements or changed requirements do pop up, the actual effect they have is quite disproportional to if you had actually just considered it in the first place. Because now you not only have to rewrite not everything, but you have to rewrite a good bit of your code or just general design. You also have to introduce those new things, and maybe you have to like come up with an entirely new paradigm. You'll find that the way that you thought your sort of limited use case now needs to expand to a completely different thing, and you have to turn it on its head. So in practice, it kind of looks like this. You start off with a build system, and then over time, you sort of get into this overextension of it. You push it beyond its limits, and then you run into trouble, and you start refactoring and retooling things, and that becomes an expensive headache. And then I think what happens a lot of the time is sort of what I mentioned earlier, which is that people create their own ad hoc solutions, their own custom build systems for their company, or maybe just for a single product. This could be like a shell script. Maybe it could be like a more fancy thing. But this is also something that takes a lot of time and energy and just can be a bit of a distraction from your actual work. Could be interesting, but I think when you want it is not when you really want to work on it. So this is sort of where a meta build system kind of comes into play. So a meta build system is nothing that fancy. It just orchestrates underlying tools. So these tools hopefully are kind of relatively small. So maybe it's just like a single compiler, or it could be, if you're exporting an SVG, it could be like Inkscape or ImageMagick or something like that. And the sort of philosophy you want with a good meta build system is to minimize the assumptions that you're making about the sort of shape of your code or your design. And in doing so, you're also maximizing the flexibility. You're letting yourself be able to change things later on because you haven't made sort of sweeping assumptions about what you're working on. And then the underlying tools that you're hopefully using sort of follow the general Unix philosophy of just performing one pretty well understood role. And in doing so, they can be substituted later on with similar components. So if you have one Rust compiler or something like that, but I guess C is a good example, or C++. If you have GCC, you might be able to substitute it with Clang pretty easily. There's nuances there, but and there's different advantages and disadvantages, but ultimately they're pretty compatible with each other, and that they can be swapped out, and you don't lose a ton of time. So the meta build system just sort of ties those all together. And of course, you can also have sort of hybrids where you have like you have a underlying tool, a smaller tool that also sort of thinks at this big level, but you'll find that like if you are using that as a meta build system, then when you actually want to swap it, you don't actually have that ability because it's making a bunch of assumptions. So this is sort of a build system taxonomy, just so that everyone knows sort of what we're talking about here. So the ad hoc build systems I talked about earlier would be things like, these are some example projects. I'm not picking on any. I think a lot of these are actually quite good, but things that are sort of shaped like shell scripts or sort of one-off programs to actually build a certain type of thing. So if you're building a Dioxys app or something like that, you would use the Dioxys CLI, and it would know things about Dioxys and be able to build for that. A lot of times you don't start with one of these, but you might end up developing when you need it. There's more domain-specific things like Cargo, CMake, Maven, Meson are pretty good examples. I think these fit sort of the Unix philosophy pretty well. I guess Rust C might be a better example than Cargo, perhaps, but they are more informed about the actual language or technology that you're working on, and they benefit from that knowledge. If the compiler knows that it's working on a sort of Rust-shaped project, it can do Rust-shaped optimizations, and you can include a lot of different things that you want to that you think you'll need later on. And then there's more generic ones. So I just called these sort of task-based. I think that's pretty fair. So Just is a pretty pure example of this. It's really just something that lets you just run some commands. I think most CI/CD systems are sort of designed like this nowadays. You have, a large YAML file, and each line can be something you want to execute. And sometimes you can have dependencies within it, and you can have different conditions, and those can be pretty powerful. But ultimately, they still kind of can be boiled down to just a task. And then sort of one level higher than rules-based, higher than a task-based, it would be rules-based, which is where you're still ultimately doing sort of independent tasks, but you might understand sort of what those tasks take in and what they put out, their sources and their artifacts. So you're compiling a C source file to an object file or a binary. I think Make is a really good example of sort of a pure example of this. So is Ninja. It's maybe more pure, but it doesn't do as much, and that's why Ninja is often used as sort of something that's generated from another project or another build system. And then meta build systems, as mentioned earlier. A lot of these are more proprietary, so Buck2 and Bazel, and they have open source equivalents, but ultimately they're usually more used inside of an organization because they have sort of a broad philosophy, and you can have everyone inside your company be able to follow that philosophy, and you can benefit from it. I think these are pretty good examples of ones that also have a lot of boilerplate, and that can be its own expense, but that's often why they're also able to be used inside of a company, because they can benefit from the customization, and they can also make people use them, and they can have sort of an industry around just learning how to use them. They also tend to attract a bit of a cult following, good and bad. So I mentioned Make, and I sort of want to talk about it briefly just because I think it's a good sort of pure example. But I think it sometimes gets a little bit more hate than it deserves, just maybe because it's older. And it had sort of it developed into something a little bit interesting. But it's a little hard to read, but it ultimately has a pretty simple idea. It's based on rules, which take essentially sources and artifacts, and they represent a transformation with a recipe. And sort of like Ninja, they're often generated as well. So this is an example of Makefile. I wonder if my cursor will appear. No. But yeah, you can see that, for example, here we're taking C files, turning them into object files, and then we have a recipe that sort of explains how to do that. It's sort of describing the shape of that transformation with a recipe. So I think that the rule system makes a lot of sense. You can optimize about it. You can make an entire build tree based on it. And it's all built on things that people are already familiar with. You may have already started by running a GCC command or similar, and now you can just put that into a recipe, and then you can sort of recreate that. And because you're using that whole like source artifact tree, you can be able to do things in parallel. You can say, oh, well, this doesn't depend on this, so I can do these two things independently. It works better for things that are more designed for it. I think like C++ compilers are a little more shaped like that. I think we've strayed a little bit more from that, at least in how things are more often used. So if you're working on a Rust project, it's most likely, unless you're working on the Rust compiler itself, you probably don't do too many invocations of Rust C exactly. But that's just kind of how things have developed. And there are some complaints about it that, maybe it's a little bit hard to read. It kind of looks like just magic if you don't really know what you're looking for. But if you read through the hundreds of pages of docs, it'll make sense, I promise. And then there's also sort of the problem that ultimately they're sort of run on shell script recipes. You actually can swap out the shell, so that can solve some problems. But sort of shell script recipes can lead to shell script problems. And so quoting rules are similar, a good example of that. I talked a little bit about Bazel and Buck2, the sort of meta build systems that are used inside Meta and Google. And they own the world. They're aware of quite a lot of things. They are aware of like maybe the entire monorepo. They're aware of all the different languages. Usually they entail a lot of boilerplate, and they don't really play well with outside tools. So I know like Meta, for example, has a project called Reindeer, which converts cargo like projects into like Buck2 projects. And those work, that works pretty well, but when you actually want to just collaborate with an outside team, now you have this sort of translation issue, which can be a problem. So what if we can do something better? The sort of target use cases that we're looking for in sort of ascending order of complexity would just be a simple task runner, sort of like Just and similar. Maybe something else we want to do is be able to do cross-platform generation of bundles, so application bundles. I think that's something that a lot of people are interested in. I have been keeping a little bit of a tally for some of the talks the past couple of days, and a lot of different projects were expressed like the sort of desire to have a better way to be able to generate bundles, and not without having to do it all themselves, without having to do all of the research and design of an entirely new build system just for that. And then, just having a multi-stage build procedure, so maybe handling assets for doing like text transformations or data transformations, something where like the native build system doesn't want to support that. It's a little bit more in detail. We want something that's expressive and flexible. We want to be able to look at it and understand what it does and know how to change it to sort of do what we might want to do in the future. Should be kind of self-documenting, in other words. We wanted to be transformation aware, so have sort of those like make-like rules. As it turns out, that ends up being a pretty good thing when you want to do optimizations later on, because if you don't actually understand sort of the what you're actually producing and what you're using to produce that, then it's hard to be able to reason about just the overall structure. And in this case, we want something that's language agnostic or framework agnostic, so we don't want to make too many assumptions about what language you might be working in. And especially, we also want to be able to support languages or projects that use multiple languages, because that is, especially with application development, you might have a JavaScript front end and a REST backend or something like that. Or you might just have a REST front end and a REST backend, but they're compiled completely differently, and that could be considered almost a multilingual project. So also cross-platform for the host as well. So you can run it on anyone's machine, and it should be roughly the same. And that is sort of also a shell script problem, because a lot of times, the shell scripting or the shell might have like certain built-ins, but ultimately you might be running a lot of things that sort of maybe assume that you're running on a certain type of Linux machine. And also, just we want the whole thing to be packable. We want it to be extensible, and so allow people to be able to put their own things into it. And we also want it to be introspectable. So we want to be able to get all the different metadata about what our build actually did. And in order to do that, we sort of produce machine-readable metadata from that. And that way we can use it in, say, an online CI/CD platform like GitHub Actions, for example. And we could have some sort of way to integrate that and be able to see, oh, this task worked, this task didn't. In short, the overall goal is to ensure that the easy cases are easy and the hard cases aren't much harder, which sounds like something that's really simple, but in practice, things don't often work out that way. So, Quake. It is a cross-platform build system that relies on currently GNU Shell, which is a shell that's written in Rust. We'll talk about it in just a second. But it uses a domain-specific language inside of that. And because it's written in Rust, we actually can introduce our own commands. It has its own library, and that can be really powerful. And we're also relying on a couple other niceties from the Rust ecosystem. I think part of Rust's popularity is owed to its good error reporting, and that's something that a lot of people have worked really hard on a lot of different ends of that. The Miet crate is an error handling and reporting library that works pretty well for this. So we can have diagnostics of different severities. We can point to where they occurred, like their spans in the code, and that works pretty well just out of the box. And we'll talk more about sort of GNU Shell's advantages. Also, this is alpha code. I've been working on other projects more recently, but there is a working version of Quake, but there's still a lot more that I'm working on. I'll talk a little bit more about that at the end. But so GNU Shell. It is also cross-platform. It has more of a functional influence than other scripting languages. It's not sort of the POSIX tradition. It's a little more data-centric. So you can read in all sorts of different data formats, whether it be JSON, TOML, YAML, whatever you want, and it converts it into its own internal representation, which you can transform using a bunch of different data manipulation tools. And so it still has like pipelines or pipes, but it's a little more functionally shaped. This is an example from their site. I think it's just honestly a really good example of how this looks. So this is sort of the internal representation. It's not the actual syntax, but it is a way of viewing the data in sort of a human-readable way. So this kind of looks like maybe like PowerShell if you use that, or maybe like SQL as well. So we still have, this is not the the ls command you might be used to. This is actually producing a little bit more parsable metadata or structured metadata. And then we can do a query on it, and we can sort it and whatnot. And it also has a bunch of other integrations. This is an example of it doing like a REST client. It also, I think, now has a whole embedded SQLite database if you want it, and a bunch of other things that you actually really might want to do inside of the build system. You might want to actually do an API request and be able to reason about the response in a structured, well-typed, or strongly typed way. So this is an example of fetching a license, which could be something that you want to do, but it could be any number of things. So this is an example of actual Quake. So here we're defining a task, and this is sort of shaped like how you would define a function inside of new shell. But instead of def, we would say def task, and we have a name, and then those brackets are where we're going to put arguments, and then we simply just have a block where we can put the actual commands to be executed. And as sort of alluded to earlier, there's a lot more built-ins inside of new shell than there are in other shells, so to speak. And I think Echo was one of those. But then, so if this is the do block, is where we execute things, then we also have a where block where we can put right before the do block. And that's sort of where we can do sort of the more declarative things that we want to do with tasks. So in this case, we're defining two different tasks, say hello and say goodbye. And say goodbye depends on say hello. So we'll say hello before we say goodbye. Both of these do something. They're loosely speaking effectful. And if we just run Quake, I guess, say goodbye, then it'll say hello first, then say goodbye. If we just want to run say hello, it'll just say hello, because there's no that dependency relationship. We can also define tasks that are just purely declarative. They have, in theory, no effects themselves. So in this case, we have two different things. We're going to check Rust format to see if all of our code is formatted correctly. And then we have a Clippy task, which just checks to see if, and because in this case, that there's no warnings. And then we have the third task, which is sort of the parent check task, and that depends on the two preceding tasks. And we could just run Quake check, and that would just work. And this is declarative, purely declarative, because it has no do block. It's just that where block. And then inside this where block, everything is still evaluated relatively programmatically. So in this case, we're actually checking to see if we are running on a Mac OS platform. And if we are, then we can put in a requires, which is essentially an assertion. We want to require that the Xcode toolchain is installed. The actual implementation of checking to make sure Xcode is installed is not put here, but you can imagine sort of what that would look like. And that requires action essentially introduces an element of fallibility. So the build task can fail, but also if the check Xcode task or check Xcode toolchain fails, then so too will the build, and it actually won't even run it first. So we won't end up with just a bunch of like missing command errors. So tasks can also take arguments, and these are shaped just like command line arguments as well. So we can have flags, we can have optional arguments, required arguments, and they actually have a type as well. And new shell will check these types. So in this case, we're just putting in strings, so it'll pretty much accept anything. But we could also take an integer if we wanted to take an optimization level, or even if we wanted to have sort of an enum where we could have, say, in the case of an optimization level, we could have z, and that would be sort of a sum type across all the different possibilities, just like an enum. And in this case, we could just run the actual implementation of this doesn't matter too much, but we can pass in these flags inside the Quake invocation, and it'll pass it into the build script as well. So Quake is structured around transformations, so tasks do have sources and artifacts. They're not required to. Like in this example, we're not defining any, but it would normally be considered good practice too, because then we can do the optimizations mentioned before. So these kind of look like this. We can define the different sources for the build task. In this case, it is reading the cargo manifest and all the different REST files in your project. Hopefully you might have a separate utility script or separate whole project that will actually do more of this magic for you. But even still, in this case, it's not that much code. And we can say what it actually produces. And if we had multiple of these, if we had multiple different build tasks, say we had building a front end and a back end, it would be able to optimize and reason about those and sort of establish a dependency relationship. But new shell itself doesn't know about, or rather Quake itself doesn't know about REST sort of before this. We're telling you a little bit about this, and we can put our own script inside of this to make that easier. Sometimes we need more advanced transformations. So this is sort of like the rules inside of make. So these are, we can transform things that kind of look like C files, or I guess these don't have any globs, but you can see like we're describing how we transform these two. We transform foo.c and foo.h into an object file, and we can explain how we do that. And then we can explain how we will transform more files into the ultimate program. I guess I don't have an example here, but you actually would be able to also use globs as well. And you could sort of define all the different files that you might want to use, or you could have those be automatically inferred. And I do have an example of that. And it can do the same sort of stuff that make does as well. So this is honestly starting to get into the realm of verbosity, and that's kind of what we're trying to avoid. We don't really want boilerplate. So we want automation, and that's where we can have utility functions and tool chains, or whatever you would like to call them. This is an example of how we can use Clang to actually generate sort of a build script for us. So the -mm flag here will actually generate sort of a make rules for us. So you actually can see the output here. Those are just sort of make like rules. And we can parse those pretty easily with new shell, because new shell is pretty good at parsing as well, as it turns out. And you can see sort of how make thinks, or rather how new shell thinks about it after we parse it. And then we can actually put this inside of a build script. And we could expand this to an entire project, but even just out of the box, it'll already understand all of these things. So you can see the transforms here. We're not specifying any explicit files. It'll just figure that out for us. So some of the future work that I've been working on, and actually I've finished most of it, is actually separating a lot of the backend, which would be just Quake and sort of how it reasons about dependencies, from the actual front end, in this case, new shell. And that allows for some really fun things. So you really could just use all the logic from Quake. You could plug it into an entirely different language or an entirely different paradigm. You could put it onto a CI/CD server, and that would just work. Or you could work on your own build system, and you could use a lot of the utilities from Quake as well. And similarly, providing more introspection for tooling, which also sort of enables extensibility. I have a fun little example here, just sort of near the end, which is what you could do if you wanted to express this in kind of like scheme shape, or Lisp, if you can read it. But this is not a particularly good example. I just had fun writing it when I was just a little bit bored. But this is entirely possible to implement. And I'm actually really excited to see how Quake could evolve using that sort of separation of the front end and the back end and everything in between. So in sort of conclusion, I think build systems and development tools more broadly should get as much attention, if not more so, than any sort of new emerging technology, because they will be constants, and they will always make everyone's lives easier. And then pretty much the same sort of idea. If other technologies, so the end products, or maybe the things you're actually building, or the underlying compilers, sort of expose more of themselves, then we can also have more interoperability with meta build systems. So this is sort of a bidirectional approach. And so if you're working on those kind of projects, please talk to me, and we can figure out some interesting ways that compilers can be used for these kind of use cases. And this is not just for Quake. This is for any number of meta build systems. A lot of different people working on interesting projects are interested in this as well. And also, just check out Quake if you're interested. I'll have some links at the end. And better yet, maybe make something better or tell me about some cool ideas. I would be very interested in hearing about them, and I'm really looking forward to what can be done. So these are my links, and that is all I have. Thank you.